Okay, this video is going to cover section 6.3, which is titled Taylor and Maclaurin series. And what's really cool about this section, it's actually one of my favorite sections in Calculus 2, is that we actually now get to really put some muscle behind all the stuff we've been learning in chapters 5 and 6, right? So in chapter 5, we learned about what a series was, and then we learned how to tell if a series converges or diverges. And then at the beginning of chapter 6, we learned about what a power series was, and that we could actually let a power series represent a function for certain values of x, and meaning that it would converge for certain values of x and maybe diverge for other values of x. The only problem is the functions that we could come up with power series for had to have the form f of x equals 1 over 1 minus x. So unless we could, as the introduction says, muscle it into that form, we weren't going to be able to find any sort of power series for a function. And in reality, not all functions are going to look that way. They're not going to look like 1 over 1 minus x. In fact, most of them don't. And that's where the Taylor and Maclaurin series comes in. The beauty of these series is they allow us to come up with power series representations for all sorts of different types of functions. And the ones we're going to focus on are some of the most common ones, like e to the x, the exponential function, and sine x and cosine x. And the concept is actually rather quite simple. So let's go ahead and take a look at where we get the idea of the Taylor and Maclaurin series. So before we can kind of start, we need to make two major assumptions. The first one is we need to assume that our function that we're dealing with, f of x, has to be a power series representation that's going to be centered about x equals a. And we know from this chapter, chapter 6, we did this in 6.1, we know that a power series representation about x equals a looks like this power series that I have in the blue box. That is nothing new. So we're going to make that assumption. Second assumption is that in order to make a Taylor and Maclaurin series, we have to be able to take the derivative of every order. So we need to be able to find the first derivative, the second derivative, the third derivative, the fourth derivative, and so on. We need to always be able to find the derivative. All right, so now that we have the two assumptions out of the way, let's talk about how we find the coefficients, because you'll notice in the power series representation that there are a bunch of coefficients. There's C0 in the first term, C1 in the second term, C2 in the third term, and so on. So let's go ahead and talk about what those actually are equal to. And it's actually rather easy how we come up with it. So if we take our power series representation, if we just look at it, notice that every term except the first term has x minus a in it. So the second term has x minus a, the third term does, the fourth term does, and so on. They're all going to have x minus a to some power. The first term does not. So what happens then if we plug a in for x? If we let x equal a, well, if we let x equal a, every one of these terms is going to go to 0, right? Boom, boom, those all go to 0 except the first term. So we can say that f of a is equal to C0. And if we solve for C0, that means that C0 is equal to f of a over 1. Now this may seem silly, why are we doing this? But we're going to see a pattern start to develop. And this is why it's important that we are able to take the derivative of every order, because what we're now going to do is we're going to take our original power series representation for f of x, we're going to take its derivative. So f prime of x, the first one, C0 is a constant, so the derivative of that is 0, right? And then the derivative of C1 times x minus a is going to be C1. Then we use the power rule on the next one, right? So if we're looking at this term right here, C2 times x minus a to the second, we're going to take the power to the front, 2 times C2 times x minus a to the first power. So we see that derivative right here. Let's talk about one more. So if we look at the next term, so the next term's right here, we take the power to the front, so we have 3 times C3 Then we drop the power down by 1, make it a squared. And of course there is a chain rule on this, but the derivative of the inside is just 1. And so we can keep on going, but the first derivative is going to look like so. And then we do the same reasoning. If we plug a in for x, this term goes to 0, this term goes to 0, this term goes to 0. All we have left is c1. And so that means f prime of a is equal to c1, which means c1 is equal to f prime of a over 1. And we could continue this pattern, so we could find the second derivative. And if we find the second derivative, that's going to mean that f prime of a is equal to 2c2, which means c2 is equal to f prime double prime of a over 2. Let's do this one more time. If we find the third derivative, and you can see it here, that's going to mean that f triple prime of a is equal to 2 times 3 times c3. So that means that c3 is equal to f triple prime evaluated a over 3 times 2. And so the question is now, if you look at all of these, right? If you look at all our constants that we came up with expressions for, do we see a pattern? Does it look like there's any sort of pattern? And I hope that you start to see it. So notice the numerator is basically the nth derivative of the function evaluated at a, and then the denominator is the value of n factorial, because in the first one n equals 0, and 0 factorial is 1. And the next one we have c1, so n equals 1. And 1 factorial is 1. So this right here is 0 factorial. This is 1 factorial. The next denominator is 2 factorial, which means 2 times 1. The next denominator is 3 factorial, which means 3 times 2 times 1. And so what we basically have is we have that c sub n is equal to, and this might be a new notation, the nth derivative, if you've never seen that before, the nth derivative of a over n factorial. And so what we can do is we can plug that back in to our power series. And when we do that, we get this definition on the next page of what a Taylor series is. If f has derivatives of all order at x equal a, then the Taylor series for a function of f at a is equal to this power series. And if you go ahead and expand that out, we get terms that look like so. So I want you to notice that it's basically the power series that we've already learned. You still have the x minus a, you still have x minus a squared in the next term, x minus a to some power for every term. But now the constant is f of a, f prime of a, f double prime of a over 2 factorial, and so on. It follows the constant. This is our constant right here, right? And so what we really need to find is, if we're going to find a Taylor series, we need to find a formula for that constant. So that's what the Taylor series is. Now the Maclaurin series says, okay, let's take our Taylor series that can be centered at any value x equals a, and let's center it at x equals 0. So that means that our value of a is 0. And when we do that, then all these become, right, if a is 0, then instead of x minus a, it just becomes x. And instead of x minus a squared, it becomes x squared. And then, of course, our derivatives, so we have f prime of 0, f double prime of 0, and so on. And so right here, this blue box is going to be our Maclaurin series. Notice it's basically just the same as our Taylor series, except wherever there's an a, we have 0. So we're going to do a couple of examples here to finish out this video, just so you can see how we actually find a Maclaurin series. All right, so example 1. It says find the Maclaurin series for f of x equals e to the x and find the radius of convergence. All right, so right off the bat, it says find the Maclaurin series. So what's that telling us? The Maclaurin series is saying that the center is 0. So the center is x equals 0. All right. So, and as I said before, the key to this is figuring out a formula for our constant expression, the nth derivative of x over n factorial. And so what I generally always like to do is set up a table to help us organize what's going on. So we can do that. We can go ahead and make a table. The first column will be n, and then the next column will be the nth derivative. And then the third column will evaluate that nth derivative at the center, which in this case, anytime you have a Maclaurin series, the center is 0. So, and then we start with 0, right? N equals 0. Our series starts at n equals 0. And let's go 1, 2, how about we do the first 4 here. And so we know that when n equals 0, that's our function. So if we let n right here be 0, then that's going to be our original function. So we know that we want to do this for f of x equals e to the x, so this is going to be e to the x. And then for n equals 1, that means the first derivative, so the derivative of e to the x is e to the x. Better make a notation of this. So just so you know, why don't we make a little note here. Note this notation means f of x, which in this case is e to the x. All right, cool. So hopefully that makes sense. Okay, the second derivative, again, if we take the derivative of e to the x, we get e to the x, and so on, right? For all of these, now it's not going to be this simple every time, but it's nice to start out simple. So those are all e to the x. And then if we evaluate each of those at 0, e to the 0 is 1, and so on, right? So this one is actually pretty straightforward. In fact, if we were to continue this on indefinitely, dot, 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 for the nth term, we know that the derivative of the nth term is going to be e to the x, and evaluating that at 0, it's going to be 1. All right, so that's kind of how we start out all these problems. And so remember, if you want to find a Maclaurin series, you want to find a power series representation for our function. And in this case, our function is f of x equals e to the x. And according to our our definition of what a Maclaurin series is this looks like a power series that has the form fn of x over n factorial times x to the n. And so if we use that formula for every single value of n, let's write out a few terms. Let's expand this a little bit. So it looks like f of 0 over 0 factorial times x to the 0 plus f prime of 0 over 0 factorial times x to the, that's not over 0 factorial, we're now on to x equals what? X equals 1. So this would be over 1 factorial times x to the 1 plus f double prime of 0 over 2 factorial times x to the second plus f triple prime at 0 over 3 factorial times x to the third plus dot dot dot. And let's just note these different values of n. So this is n equals 0. This of course is n equals 1, n equals 2, n equals 3, and so on. And so if we actually calculate this, right, we know what f at 0 is. We can see it over here in our column, right? F of 0 is 1. So we have 1 over 0 factorial. We know 0 factorial is equal to 1. So we have 1 over 1 is 1 times x to the 0, which is 1. So that first term, basically everything there is 1. We move on to the next one, f prime of 0 over 1 factorial is basically just 1, right? Times x to the first is x. We move on to the third term. F double prime of 0 over 2 factorial is 1 over 2 times x squared. And then we have plus f triple prime of 0, which is 1 over 3 factorial times x to the third. So it probably makes sense here for us to just think about this as, instead of 2, we know 2 factorial is 2. Let's write that as 2 factorial. And so you can see the pattern there. We actually have a specific power series. We're following this formula. We know that the nth derivative evaluated at 0, and I see there's a typo up there. This right here should not be an x for the Maclaurin series. Even up above up here, we should write this as 0. That should be a 0 there, and this should be a 0 here. So the nth derivative, of the function evaluated at 0 is 1. So that numerator is always going to be 1. The denominator is always going to be n factorial. And then we have x to the n. And so that is our power series. We know that e to the x is equal to 1 over n factorial times x to the n. And the question is e to the x equal to that power series for all values of x, some values of x? Well, in order to do that, we need to find the radius of convergence, right? So this is something we've done. We can go ahead and find the interval of convergence. Now, if we have a series that looks like x to the n over n factorial, what test should we use to go ahead and determine the radius of convergence for this sort of test? We have x raised to the n factorial. Well, that is going to be the ratio test, right? So using the ratio test, we have that rho is equal to the limit as n approaches infinity of x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. And when you simplify that, you get the limit as n approaches infinity of basically x over n plus 1, right? And as n approaches infinity, this sucker is going to approach 0, which is always less than 1. Now, remembering what we talked about in section 6.1, what does that mean about our r? That means it's going to converge for all values of x, because no matter what value of x we were to plug in right here, no matter what value of x we plug in there, rho is always equal to 0, which is always less than 1, so it's always going to converge, which means r is equal to infinity. That means for every single value of x, e to the x is equal to this infinite sum, this power series. And so that is a pretty cool thing. Now let's see like what this actually means with the Maclaurin series. So look at the first term. If we take the first term, n equals 1, we get 1. It's just a constant. If we take the second term, we get 1 plus x, which is a line, right? And then the third term should be 1 plus, if we take the first three terms, we get 1 plus an x squared. And if we take the first four terms, we get a cubic. So watch what happens here. Notice we have our function f of x equals e to the x. And then we have that power series we just wrote. So we have x to the k over k factorial. Now we wrote it with n's, but it's all right. And notice when n equals 0, all we have is a red line here for our Maclaurin series. It's just when our first term is just 1. Okay, so that's what you see here. Y equals 1. Now, if I drag it to n equals 1, look what happens. Now we get that line x plus 1. This is f of x equals x plus 1. It doesn't really look like it follows e to the x. E to the x is this black line. In fact, look at the error here with this blue line. But now watch what happens as n gets bigger, as we add more and more terms to our series. N equals 2. There's our red quadratic. The error is getting better. Next one is going to be a cubic. Oh, look at it, it's getting better and better. Fourth power, the first four terms, first 5 terms, and look at how that red graph is starting to fit the e to the x, the black e to the x curve, and we keep going. Fits it better and better and better and better. And so that's just the first 10 terms. Now this is an infinite power series, right? Which means there's an infinite number of terms. So as we add more and more terms, the red curve is going to continue to be closer and closer to the actual e to the x curve. And because it converges for all values of x, it will follow the e to the x curve for all values of x. And so that is the idea of a Maclaurin series. Now what I would like to do is do one more of these, and then we'll go ahead and end this video. So example 2, find the Maclaurin series for f of x equals sine x and find the radius of convergence. So we're going to go through the same steps here. We have our n's, values of n. We're going to make this table again. We have our values of n. We have our nth derivative at 0, or let's just, the second row is at x. And then the third row is our nth derivative evaluated at 0. And then we're going to go through. So we have 0, let's go 1, 2, and just like the last one, let's go through 4. So we have 3, 4, and then we'll go dot, dot, dot. Okay, our original function is sine x. If we take its derivative, we get cosine x. If we take the derivative of that, we get negative sine x. If we take the derivative of that, we get negative cosine x. And if we take the derivative of that, we get back to what we started with, sine x. And then we can evaluate each one of these at 0. So sine of 0 is 0. Cosine of 0 is 1. Negative sine of 0 is 0. Negative cosine of 0 is negative 1. And then back to 0. And so this pattern will continue on. And so what we want to do then is, again, we're trying to come up with a Maclaurin series representation for sine of x. And we know that this is going to be equal to, again, we're following that power series representation for a Maclaurin series. So the first term is going to have 0 in the numerator over 0 factorial times x to the 0. And then we have 1, right? That's right here. This is 1 over 1 factorial times x to the first. Then the next numerator is going to be 0. So we have 0 over 2 factorial times x to the second, plus, we move on to the next value of our derivative evaluated at 0, right? So f So when n equals 3, we get negative 1 over 3 factorial times x to the third. And we could keep going here, so we follow this pattern for 4 factorial times x to the fourth plus 1 over 5 factorial times x to the fifth plus 0 over 6 factorial times x to the sixth. Let's do one more. Plus negative 1 over 7 factorial times x to the seventh plus dot, dot, dot. Right? So we have all these terms. And the thing is for each one of these, I guess it's the even terms, right? N equals 0, n equals 2, n equals 4, n equals 6. For the even terms, they're all going to go to 0. The odd terms are what we're going to keep. N equals 3, n equals 5, n equals 7. Those are the ones we're going to keep. So since the even terms go away, let's go ahead and rewrite it. So let's say this. When we clean out the 0 terms, we get that sine of x is equal to basically 1 over 1 factorial times x to the first minus 1 over 3 factorial times x to the third. Right, so I'm just, oops, didn't mean to do that. To highlight, so we just get these terms I'm highlighting here in yellow. So if we just write out those terms, I want you to notice a couple things. Number one, that these terms are alternating back and forth between positive and negative. So we have an alternating series. And it's also just the odd terms. Now, this is something you just kind of need to get used to. The way we represent something as odd, to get the odd terms, you're usually going to either use 2n plus 1 or 2n minus 1. You're going to use that for odd terms. And actually, when you have even terms, you're going to use 2n. Right? 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. So it gives you the even terms. So in this case, we're going to actually want to use 2n plus 1 because we're starting with 0. And so essentially what we have is when n equals 0, we have 2 times 0 is 0 plus 1. That gives us this first one. So essentially this, it kind of, we renegotiate things, and this is now n equals 0, this is now n equals 1, and this is now n equals 2, and so on. And when we plug those values into 2n plus 1, we're going to get exactly what we want. And so our power series representation is we're going to have this from n equals 0 to infinity of 1 over, and then we have basically 2n plus 1 factorial times x to the 2n plus 1. That gives us the odd terms. So you can double check to make sure that works, but as you plug in each value of n, you're going to get these successive terms. Now the one thing we're missing is we don't have the alternating part down. So we actually need on the top a negative 1 to what power? We need the first term to be 0, right? Or we need the first term to be positive. So if we need the first term to be positive, what are we going to put there? Negative 1 to the n, would that work? So negative, if n is 0, negative 1 to the 0 is positive 1. And then when n equals 1, we get negative 1 to the first power. That's going to be negative. Yeah, that'll work. So that's going to be our power series representation. We have negative 1 to the n over 2n plus 1 factorial times x to the 2n plus 1. And of course, we do need to find the radius of convergence. So we can again use our ratio test for this one. So we have rho equals the limit as n approaches infinity. And we have negative 1 to the n times x to the 2 times n plus 1, which is going to be 2n plus 2 plus 1, or 2n plus 3, which is also going to make this on the bottom 2n plus 3 factorial, right? And then times 2n plus 1 factorial over, this should have been an n plus 1 here, negative 1 to the n times x to the 2n plus 1. Now, because it's an absolute value, we don't really care about the negative ones, right? Absolute value is going to make that all positive, so we can just ignore that. And then simplifying, we are going to get the limit then approaches infinity. On the top, we're going to get x to the, everything's going to cancel except we're going to get an x squared left. And on the bottom, remember, now this is important. If I kind of do this on the side, right? So remember, 2n plus 3 factorial means 2n plus 3 times 2n plus 2 times 2n plus 1 times 2n. So basically times 2n plus 1 factorial. So that means we're left with, when we cancel out with the 2n plus 1 on the top, we're left with 2n plus 3 times 2n plus 2. And again, as n approaches infinity, the denominator is going to go to 0. So this limit is going to give us 0, which is always less than 1. So r is going to be equal to infinity. We're going to have a sine of x is equal to this power series for all values of x. And we can see that, again, in Desmos, if I go to this other demonstration, and I increase the number of terms, watch how our power series, watch how the red line starts to match the black sine curve. N equals 1. The more terms we go out, the bigger the convergence is. The closer the red curve gets to the black curve, and if we had an infinite number of terms, it would be exactly equal to the sine curve. So that's the idea with the Maclaurin series, and that's going to end this video. Hopefully everything made sense. If you want to see those visualizations in Desmos for yourself, you can go ahead and click on the links here right in the notes, and it'll take you to those. But that's what I got. Thank you very much.